Hello, everybody, and here we are starting the introduction to elimination reactions and the preparation of alkenes and structure of alkenes. And we've talked already about substitution reactions, where we could take a leaving group and we can substitute for it some nucleophile like hydroxide and replace it and make the alcohol. Now, in the elimination chapter, what we do is instead of replacing the bromine or replacing the leaving group with the nucleophile, in this case hydroxide, can grab the hydrogen on the adjacent carbon, form the double bond, kick off the leaving group, and we have to be very careful that we do how we do this, because there is still a hydrogen on the carbon with the leaving group. So we have to be careful how we draw the mechanism so that we get it correct, but we end up replacing or eliminating to form a carbon-carbon double bond. In every elimination, we will form some sort of carbon-carbon double bond. Okay, so be very careful about that we get a carbon-carbon double bond out of all the elimination reactions. So first we'll start off with nomenclature, and if we have a hydrogen on each side of the double bond, we can name it with either cis or trans. And if you think about laying your pencil down the center of the double bond, if the hydrogens are on the same side, it's cis. If the hydrogens are on opposite side, it's trans. So this is a trans alkene, and we have a 1, 2, 3, 4, 5, 6, 7, 8. So it's octene, and off of that octene we have a 2,5 dimethyl, and then the octene is on carbon 3, so 3 octene. On the next one we have 1, 2, 3, 4, 5, 6 carbon, so it's a hexene, and the double bond is on carbon 1, and on carbon 1 we have 2 hydrogens on it, so we have 2 of the same thing, so we don't have to say cis or trans, it's just one hexene. The next one is a cyclo. It's a 6-membered ring, so it's a cyclohexene, and anytime we do this, in this one it doesn't matter, but we always number through the double bond, and so the double bond, since that's all there is, it has to be on carbon 1. We don't have to say that. It can just be cyclohexene, and it is cis cyclohexene, but that also is the only way cyclohexene can exist, so we don't trans necessarily have to say that. If we don't have a hydrogen on each side of the double bond, we need to use E or Z, and Z is for zusammen, or same side, and E is for entgegen, or opposite sides, and we have to figure out what the highest priority group is on each end of the double bond. So for example, on this one, bromine versus ethyl, the bromine is the higher priority. Chlorine versus ethyl, the chlorine is a higher priority, so they are on opposite sides. So it's E for entgegen, and then 3 bromo, 1, 2, 1, 2, 3 bromo, 4 chloro, 3 bromo, 4 chloro, 3 hexene. And the next one here, 1, 2, 3, 4, 5, 6, 7. So it is a 3 heptene. And off of that 3 heptene, we have a 3 bromo, 4 methyl. And then we have to think about, is it E or Z? And we have bromine versus ethyl. So the bromine is the higher priority. And on the other side, we have a methyl versus the propyl. The propyl is a CH2 here connected to another CH2, whereas this is a CH3. So the propyl is higher. So we have the bromine on one side, the propyl on the other. So this is an E. 3 bromo, 4 methyl, 3 heptene. In this one, while we can say cis for both of them, we can also use the Z, and if we number through one of the double bonds, we see it is A 1Z 5Z, and then 1,5 cycloocta, excuse me. Octadiene. And then the next one here, we have two double bonds again. On the first one, we have a hydrogen versus a ethyl, so the ethyl is higher. On the second, on the other end of it, we have methyl versus all of this, so this is all higher. So the first double bond is going to be an E, and then we'll erase all of this so we can talk about the second double bond. On the second double bond, the bromine on this side versus this carbon, the bromine's higher. And on this end, it's methyl versus propyl, so it's this side. So both double bonds are E. So then if we number through 1, 2, 3, 4, 5, 6, 7, 8, 9, it is a 3,5 nonadiene. Nonadiene, and off of that 3,5 nonadiene, we have a methyl at carbon 4 and 6, and a bromine at carbon 5, so 5 bromo 4, 6 dimethyl. And then out in front of all of that, we have to say that a carbon 3 E and carbon 5 E. And then down here we talk about the substitution pattern of double bonds. Mono-substituted has one alkyl group. A di-substituted will have 2. Tri will have 3. And a tetra will have 4. And of these, the least substituted one, the mono, is least stable, whereas the tetra substituted is most stable. So as in the last chapter, we had two mechanisms, the SN1 and the SN2. One could go through the direct substitution, the SN2, where you had substitution nucleophilic bimolecular. Here we have E2, where it's elimination bimolecular. The base and the compound with the leaving group have to come in contact at the same time, whereas the E1, all we need is our alkyl leaving group in the rate determining step to form the cation, just like in the SN1, and then the base will come in and grab the hydrogen. So the first step of the E1 is the rate determining step. The only step of the E2 is the rate determining step. So in these, if we look down here at the bottom, which of these, the primary leaving group or the tertiary leaving group, is going to go best via an E1 or an E2, or a bimolecular or a unimolecular reaction? And it was said before, the tertiary compound will be best for the unimolecular reactions because they have to go through the cation, whereas the primary one would be better for the bimolecular reaction. So here we have the two mechanisms for an elimination, and as we already said, the hydrogens come off of the adjacent carbon, and if we draw the hydrogens in on our starting material and product, we can see that the end carbon, the carbon with the leaving group, had two hydrogens on it, and the N carbon in our product still has 2 hydrogens on it. So our base has to grab a hydrogen off of the carbon adjacent to it, forming the double bond, kicking out the leaving group all in one step to give us the alkene. So this had to be an E2 because we have a strong base, weak nucleophile in our T-butoxide. So when we draw the reaction coordinate diagram, it's going to have one hump where the transition state happens to have the T-butoxide forming a bond to the hydrogen, which the hydrogen is breaking a bond to the carbon. The carbon is forming a double bond to the carbon next to it, and then the leaving group, the chlorine, is leaving, and then we have our hydrogens, and on the back carbon we have our hydrogen and our 3-carbon chain. And all of this is our transition state for this. And we have a partial negative on our T-butoxide and a partial negative on the chloride. And then our starting material is right here, and our product is down here, partially covered up by our transition state. Now in the E1 mechanism, we know we have to form the cation. So to form the cation, we need a solvent that helps to form the cation, a polar protic solvent, to stabilize it. And then once we form the cation, then our solvent, the methanol, can grab a hydrogen, forming the alkene, giving us our product. So in our reaction coordinate diagram, the first step is going to take a lot of energy. The second step won't take near as much energy. So we have our product down here, our alkene, our starting material here. In the intermediate, we have our cation, and then our first transition state, we have the bond between the carbon and the chlorine breaking, with a partial negative forming on the chlorine, a partial positive forming on the carbon. So this is transition state number 1. In transition state number 2, we have our intermediate, the cation, turning into the alkene. So we're going to have in the cation, everything is in the same plane because it's the center carbon is sp2 hybridized, and in our product, the center carbon is sp2 hybridized, so they are trigonal planar. So what happens in the transition state is we have the bond lengthening out to the hydrogen, the double bond forming, and our methanol forming a bond to the hydrogen on the carbon. So we have a partial positive on our central carbon and a partial positive on our methanol oxygen, and that gets us to the product.